Hi class, me Mr. Morris again. We are doing some example problems regarding deviations from the ideal gas law. So this question asks us, the ideal gas law best describes the properties of which of the following gases at 0 degrees Celsius and 1 atmosphere. So the question is really wanting to know if it's the same conditions, which of the following gases is going to be the most ideal. So what we want in an ideal gas, for a gas to be ideal, is it has the fewest electrons. That's going to reduce its London dispersion forces. And it also needs to be, the fewest electrons and nonpolar. That's going to reduce the dipole-dipole forces or hydrogen bonding forces if that applies. So that talks about the intermolecular forces side. In addition to that, we also need to think about the volume it takes up. So we also want the smallest molecule. So looking at these structures, we can kind of deduce which ones are ideal, which ones are not ideal, and rank them in order if we wanted to. Let's just kind of start by looking at the first one, NH3. So NH3, if we were to draw its structure, it's going to look something like this. Now I did that kind of from memory, but really if we wanted to go through and draw it out, we would see that there's 5 electrons, 5 valence electrons for nitrogen and 3 for hydrogen, so that gives us 8. I'd draw nitrogen with 3 hydrogens, connect each one with a bond. That gives us 6 electrons, the last 2 go on nitrogen. You can see that this lone pair of electrons on top makes it a polar molecule. So this one is polar. That makes it not ideal. Okay, so that helps us out with deciding it's not NH3. Okay, we could look at the next one, HCl. So HCl has 1 valence electron, and chlorine has 7, so that would be a total of 8 valence electrons again. So we have HCl. It's got the same number of valence electrons. And chlorine is far more electronegative than hydrogen is, so this is also polar and not ideal. So we could go on and we could draw O3. So that one doesn't look like it's ideal. O3 has 1, 2, 3 oxygens, and each of those has 6 valence electrons. 6 times 3 is 18. So let's see, 2, 4, 6, 8, 10, 12, 14, 16, and then we get 18. Now, the outer atoms have enough electrons, but the one in the middle doesn't. This actually has resonance because I could take 2 electrons to share them as a bond from either of the outside oxygen atoms. I'm going to choose the one on the left, but you could have just as easily done this with the one on the right. When you draw it this way, you can see that it's a bent molecule, and we have 2 oxygens on one side and 1 oxygen on the other. That's going to lead to this being a polar molecule, because one side is going to be more electronegative than the other in this bent molecule. It's polar, and that makes it not ideal. That's supposed to be a parentheses, not a C. Sorry about that. This is also not ideal. Now it's a little bit better. This would actually be more ideal. NH3 is probably the least ideal because it's also a large molecule. It's a large molecule that's also polar. So I think they're probably written in order, but let's look at oxygen, O2. So O and another O. There's a total of 12 valence electrons, so we have 2, 4, 6, 8, 10, 12. Now, it looks to me like we have one unhappy oxygen atom, so I need to share electrons from the more abundant, from the oxygen that has more valence electrons. Make a double bond. 2, 4, 6, 8, 2, 4, 6, 8. And you can see this is a linear structure where the electrons are shared evenly. This is nonpolar. It's the most ideal. So that's the answer of the first one. All right, which of the following gases will deviate the most from the ideal gas law? Deviating the most means that it needs to be the least ideal. So if it says deviate the most from the ideal gas law, what we're looking for is the least ideal. Now this one is a little bit different because all of these are nonpolar. Now if you have a bunch of nonpolar molecules, the only thing that we could do is compare the size of the electron cloud or the number of electrons. So since they're all nonpolar, we're going to compare the total number of electrons. So H2, that's hydrogen. We've got 2 of them, so that means we're going to have 2 electrons. So hydrogen has 2 electrons. Nitrogen is going to have 7 times 2. We're not talking valence electrons, this is total number of electrons. So this one has 14 electrons. Fluorine has 9 times 2, that would be 18 electrons. And chlorine, Cl2, has 17 times 2, which is 34 electrons. The one with the most electrons is chlorine. So chlorine, having the most electrons, is going to have the greatest LDF. Cl2 has the most electrons, so it has the strongest LDF, which is, in this case, the strongest IMFs. And remember, the IMFs are the stronger the IMFs, the less ideal they are going to be. So we could say, therefore, Cl2 will deviate from the ideal gas law the most. All right, our next one says a vessel contains krypton. It contains krypton gas at high pressure. Which of the following statements best helps explain why the measured pressure is significantly greater than the pressure calculated using the ideal gas law? So this is actually taken from a multiple choice question, but what we want to do is identify what are some reasons that maybe krypton would have krypton at high pressure would have a measured pressure significantly greater than expected. Why would its pressure be greater than expected? Well, let's look at what krypton is. Krypton is right here. It has 36 electrons. It's nonpolar. It has 36 electrons. It's a pretty big atom. Okay, So it's a fairly large atom. So Kr has a large electron cloud. So the actual volume available for Kr particles to move around is less than the volume of the container. So the pressure observed would be greater than the pressure of an ideal gas. And the reasoning for that, again, is because you have less volume, and remember, pressure and volume are inversely related. So let's look at the next one. The table below contains information about samples of 3 different gases at 273 Kelvin. The samples are 3 identical rigid containers numbered 1 through 3, so they have the same volume. What's the best explanation for the lower pressure in container 3? So why would the pressure be lower in container 3? So we've got identical samples, it looks like, very close to the same masses between these two. This one has a greater mass, but look at the pressure being different. What would the reason be? Why is it that container 3 has a lower pressure? Why would it have a lower pressure? Well, we want to look at what makes this one different. CH4 and Ne are both nonpolar, but let's look at SO2. SO2, well, sulfur has 6 electrons. Oxygen has 6 valence electrons, so 6 times 3 is 18. So that's 2, 4, 6, 8, 10, 12, 14, 16, and then we've got 18 there. Sulfur's not satisfied, so we're going to have to move 2 electrons from one of the 2 oxygens to make a double bond. But you can see, I hope, that this is a bent molecule, so this is a polar molecule. Since it's a polar molecule, that means it has dipole-dipole forces. It has stronger LDF, or not LDF, it has stronger IMF than Ne or CH4. Okay. And because of that, you have stronger IMF. Remember, that slows particles down before colliding with walls of the container. With the container walls. And decreases pressure. So that would explain why we would have a lower than expected pressure. Lower pressure with SO2 than the other two because SO2 is less ideal. Alright, so we've got a summary page right here. I'm going to pause the video here and have one last video that just sums up everything we've talked about in these notes.